Okay, let's dive in. Today we're tackling a language that, well, it's pretty much everywhere. Java. I mean, this thing is the backbone for so much, right?
Yeah.
Your Android phone, complex banking systems, web servers. Our mission here for you listening isn't just a feature list. We want to really unpack the insights, the why behind Java's huge impact. We've got some great source material to work from.
Yeah, and what's really fascinating, I think, is how it got there. It wasn't just like smart coding. It feels like there was this foresight about where computing was heading, especially distributed systems. Our sources really let us peel back those layers, get beyond the what to the why.
Okay, so let's start right there. What is Java, fundamentally? And, what problem was it actually built to solve back in the mid-90s? Our research points to it being high-level, object-oriented, platform-independent, came out of Sun Microsystems, James Gosling's team, 1995. They were aiming at consumer electronics initially, weren't they? Reliability, portability needed to be top-notch.
Exactly. Way beyond just desktop software at the time. Then JDK 1.0 drops in 96, then boom, it just
Yes.
took off.
Yeah.
Desktop, web backends, you mentioned Spring, huge there, enterprise. Mobile with Android.
Right, and that huge spread connects straight back to that famous promise, write once, run anywhere,
Right.
or you are. But let's dig into that. It sounds revolutionary, and it was. But what are the practical realities or maybe challenges of actually making code run anywhere?
That's the million-dollar question, isn't it? See, unlike C or C++ Lisa, which compiles straight to machine code for, say, Windows or Linux, Java does something different. Your Java code gets compiled into this intermediate thing called bytecode.
The dot class file.
Exactly. And these files aren't tied to a specific operating system. Instead, you have the Java virtual machine, the DVM. Think of it as a software layer, a translator. It takes that bytecode,
And translates it on the fly.
right, translates it into the actual machine code for whatever operating system it's currently running on, Windows, Mac, Linux, whatever. So, in theory, your app just works everywhere.
So the JVM is like this universal adapter. But you mentioned challenges, nuances. Where does the theory maybe hit reality?
Well, yeah. While the bytecode is portable, the JVMs themselves can differ slightly. Different vendors, different operating systems. Sometimes you see subtle differences in performance or how OS integrations work. And then there's the JIT compiler just in time.
Ah, the optimization part.
Right. The JVM is constantly optimizing that bytecode as it runs. But how it optimizes isn't identical everywhere. So an app tuned perfectly on a Linux server might need, some JVM tweaking to run just as well on Windows. It's powerful, definitely, but not quite a magic wand for identical performance everywhere, always.
That's a really important distinction, running versus running optimally. And our sources break down the pieces, the JDK, the development kit, for actually building the code.
Right. That includes the compiler, javac, and the Java command to run things,
Then the JRE, the runtime environment, just for running apps.
which is basically the JVM plus the standard libraries.
And that crucial JVM we've been talking about. Okay. Beyond WRA, Java also pushed things like automatic garbage collection. For listeners maybe wrestling with memory management in C++ code, that sounds like a dream. But what's the deeper story with Java's robustness and security?
Garbage collection, yeah, it's a huge plus.
Yeah.
Developers don't have to manually free up memory, which cuts down on a lot of common bugs like memory leaks.
Mm-hmm.
Big win. But, and this is key for performance-sensitive stuff, it's not totally set and forget. You often need to understand the different GC algorithms, G1, ZGC, others, and maybe tune them using JVM flags to get the best latency or throughput.
So it can introduce pauses if not tuned right.
It can, yeah. A poorly tuned GC can definitely impact user experience.
Yeah.
As for robustness and security, they're kind of baked into the design. Robustness comes from strong type checking at compile time and the whole exception handling structure, which forces you to think about errors. Security is built around the JVM sandbox model, limiting what code can do, and things like bytecode verification, checking the .class files for, bad stuff before running them.
Okay, so it shifts the burden, but doesn't eliminate the need for understanding, especially for optimization. Makes sense. All right, let's zoom in from the big picture architecture down to the nitty-gritty, the actual building blocks. We won't list every single primitive data type. Our audience gets that, but maybe some interesting implications. Like char in Java being 2 bytes for Unicode. Why was that significant?
Well, that was huge. And quite forward-thinking back then. C's char was typically 1 byte, ASCII-focused mostly. Java going with 2 bytes, natively Unicode, meant it was built for internationalization right from the start, handling different languages, different scripts, much less painful than in older languages. Make global apps, way easier.
Okay, cool. And we store this data in variables. Thinking about structure, how does Java handle variable scope, where a variable is alive and can be used?
Right. Scope is fundamental.
Mhm.
It dictates visibility and lifetime, which impacts memory. You've got local variables declared inside a method. They live on the stack, very temporary, only visible in that method. Good for keeping things tidy, modular.
Prevents messing things up elsewhere accidentally.
Exactly. Then you have instance variables.
Hmm.
These belong to an object of a class. They live on the heap, and each object gets its own copy. That's core O. Each object has its own state. And finally, static variables. Declared with static, these are shared by all objects of that class.
Like a company name for all employee objects, maybe.
Perfect example. They live in a special area of the heap tied to the class itself, not individual objects.
So local on the stack, fast in, fast out. Instance and static on the heap longer life, managed by the garbage collector we mentioned. That really shapes how you organize data.
It absolutely does. And understanding that heap versus stack distinction is key. Static variables, for instance, while useful, you have to be careful in multi-threaded situations. If multiple threads try to change a static variable at once,
Uh-oh. Race condition?
yep, unless you use proper synchronization. So convenience comes with considerations.
Always trade-offs. Okay, so we have data. Now we need logic decisions. Loops. We all use operators, if statements for loops, but maybe less obvious stuff. Any common traps or best practices in Java when dealing with complex logic, like operator precedence or choosing switch versus if-else if?
Oh, definitely. Operated precedence, that's a classic bug source. You forget parentheses, and suddenly a plus BC does something totally unexpected. My advice, just use parentheses generously. Makes it clear, even if technically not needed.
Readability counts.
Always. For switch versus if, else if. Switch has gotten pretty powerful in modern Java, especially with switch expressions. It's often cleaner for multiple fixed conditions, especially with enums or strings. Sometimes faster too. Compiler can optimize it. But if else if is more flexible for complex conditions, ranges, things that aren't just simple equality checks. Oh, and the scanner for input. Great tool, but easy to forget to. Close it. Resource leak, a common rookie mistake.
Right. Those little details add up to robust code. Good points. Okay, this brings us to the really core stuff, Java's whole philosophy. Object-oriented programming. Oh, OP. This isn't just features, it's a way of thinking, right? It changes how you approach building complex software. Starts with classes and objects. Class is the blueprint, object as the actual thing built from it. What's the deeper value of this approach in big systems?
The blueprint analogy is spot on. The deep value is that classes bundle data and the behavior that acts on that data together. Encapsulation, which we'll get to. Instead of functions scattered everywhere messing with global data, you group related stuff inside objects. It makes things more modular, easier to understand, test, reuse. You're modeling the problem domain more directly in the code.
Easier to wrap your head around complex systems that way. And a key part of creating these objects, constructors. They're more than just special methods, aren't they? Kind of like gatekeepers for an object state.
Absolutely gatekeepers. Vital. Constructors guarantee an object starts its life in a valid, predictable state. Without them, you could have objects with, like, null values where they shouldn't be, leading to crashes later. The compiler gives you a default one if you don't write any, but defining your own lets you enforce rules, set initial values, inject dependencies, essential stuff.
And this keyword plays a big role here.
It does. Most obviously, it distinguishes between an instance variable and a parameter with the same name inside the constructor. This.name equals name, that pattern. But this, with parentheses, lets one constructor call another constructor in the same class. That's constructor chaining. Super useful for reducing duplicate setup code if you have multiple ways to create an object.
Ensuring consistency. Very cool. Okay, so constructors set things up right. Now, the big OOP principles that structure the code, clarity, security, reuse, let's hit encapsulation. Often explained as data hiding, private variables, public getter setters. What's the bigger picture gain for, say, long-term maintenance or designing APIs?
It's way more than just hiding. It's about controlling access and managing change. By making variables private and only allowing access through public methods, getter setters, you create a stable interface. You, the class designer, can later change how that data is stored internally, maybe optimize it, change the type, without breaking all the code outside your class that uses it.
Because they only ever interacted with the public methods, the contract.
Exactly. It decouples the internal implementation from the external usage. That's crucial for maintainability and building flexible APIs. You promise a contract, but keep internal freedom.
Nice. Okay, next, inheritance. The ISA relationship. Child class gets stuff from the parent. Great for reuse. But Java famously doesn't allow inheriting from multiple classes. Why not? And how do interfaces provide a workaround?
Right, no multiple class inheritance. That was a deliberate choice to avoid the diamond problem. Imagine class D inherits from B and C, and both B and C inherit from class A. Now, if A has a method and both B and C override it, which version does D get? B's or C's? It's ambiguous. Java sidestepped that whole mess for simplicity.
Okay, makes sense. So, interfaces.
Interfaces solve this differently. They provide multiple inheritance of type or contract, not implementation, at least not primarily. An interface says, if you implement me, you must provide these methods. A class can promise to fulfill multiple contracts by implementing multiple interfaces. It gets the what, the method signatures from multiple sources, but provides the how, the implementation itself, avoiding the conflict. It enables polymorphism across unrelated class hierarchies, very powerful for flexibility.
So, inherit implementation from one parent class, inherit contracts from multiple interfaces.
Got it.
And tools like super and at override help manage inheritance.
Absolutely essential tools. Super lets you explicitly call the parent class's constructor or method, avoiding ambiguity and ensuring parent logic runs when needed. And at override is like a safety net. You tell the compiler, I intend to override this method. If you misspell it or the parent method changes later, the compiler catches it. Saves so much debugging time.
Little annotations making a big difference. Cool. This leads smoothly into polymorphism, many forms. Method overloading versus method overriding. For our listeners, what's the practical design difference? When do you use which?
Good question. Overloading is compile-time polymorphism. Same method name, different parameter lists, different types or number of arguments. It's mostly about API convenience, like having multiple printl methods that can handle strings, integers, whatever. The compiler figures out which one you mean based on what you pass in.
So flexibility for the caller.
Right. Overriding, on the other hand, is runtime polymorphism. This is where a subclass provides its own specific version of a method that's already defined in its superclass. This is huge for frameworks and extensible design. A base class defines a general action, say draw shape, and subclasses like circle or square provide their specific draw shape implementation. The actual method that runs depends on the actual object type at runtime. That's dynamic behavior, super powerful for flexibility.
Okay, overloading for convenience, overriding for specialized behavior decided at runtime, clear distinction, and the last pillar, abstraction, hiding the messy details, showing only essential functionality. We use abstract classes and interfaces for this. How does a developer choose between them, especially since interfaces got default methods in Java 8?
Ah, yes, the lines have blurred a bit, making the choice more about design intent. Historically, abstract classes were for partial abstraction. They could have instance variables, concrete methods, and abstract methods, no implementation. Interfaces were pure contract, only abstract methods. Now, with default methods, interfaces can provide implementation too. So the choice is more like use an abstract class when you have a group of tightly related classes sharing a common base state and some implementation. It's a strong ISA relationship defining a core identity.
Like different types of account all sharing some common account logic?
Exactly. Use an interface when you want to define a capability or contract that potentially unrelated classes can implement. Think runnable, comparable, serializable. It's more about can-do or has-a. Interfaces are better for loose coupling. Default methods are great for evolving APIs without breaking existing implementers. You can add a new method with the default behavior.
That default method feature really was a game changer for evolving libraries. Makes sense.
It really was. Oh, and briefly, the final keyword fits in here too. Final on a method means it cannot be overridden. Final on a class means it cannot be extended. Locks down parts of the design. And never forget the object class. Every class in Java implicitly extends objects. So methods like toString, equals, hashcode are always there. You often need to override them thoughtfully for your objects to behave correctly, especially in collections.
Right, even the base object gives you stuff to think about. Good reminder. Okay, shifting gears slightly. Beyond the core language and OOP, Java has this massive ecosystem for real-world tasks. Let's touch on a few key areas essential for big applications. The collections framework, java.util. More than just a array list, right? What's the power, or maybe a common pitfall?
Oh, the collections framework is incredibly powerful. Optimize data structures for everything. The hidden power is understanding the trade-offs. Array list versus linked list, one's fast for access, the other for adding removing in the middle. Hash map versus tree map, one's fast for lookups, the other keeps things sorted. A common pitfall is just using array list or hash map for everything without thinking if it's the right tool for the specific access pattern, leading to performance issues down the line. And generics, using them correctly for type safety, is crucial.
Choosing the right tool for the job. Classic engineering principle. Okay. How about exception handling? Beyond just try catch, what's the deeper design insight in Java's approach?
The key is the distinction between checked and unchecked exceptions. Checked exceptions, like IO exception from file operations, force you to deal with them. Either catch them, try catch, or declare that your method throws them. This makes APIs more robust because potential expected failures are explicit in the method signature. It's part of the contract.
Forces you to acknowledge something might go wrong.
Yep. Exactly. Unchecked exceptions, null pointer exception. Array index outbounds are typically programming errors, logic flaws. The compiler doesn't force you to catch them because ideally you should fix the underlying bug. Understanding when to use which or how to handle them is key to designing resilient systems.
So it's a disciplined way to communicate and handle errors. Makes sense. And finally, in today's world, concurrency and threading, multi-core processors everywhere. What's the main challenge here, and how does Java help?
Concurrency is hard, period. The main challenge is managing shared, mutable state safely across multiple threads, avoiding race conditions, deadlocks, making sure changes in one thread are visible to others. It's complex. Java helps immensely, though. It has built-in synchronization using the synchronized keyword, but even better is the java.util.concurrent package. It provides higher-level tools, thread pools, executors, thread-safe collections, concurrent hash map, atomic variables. These make writing correct concurrent code much, much easier and often more performant than low-level locks.
So providing tools to manage the inherent complexity.
Yeah.
Got it. These capabilities really underscore why Java is so dominant in enterprise.
Wow. Okay, we have covered a ton of ground today. From Java's origins, that write once run anywhere idea and its nuances, through the deep concepts of OOP encapsulation, inheritance, polymorphism, abstraction, and finally touching on its powerful ecosystem for collections, exceptions, concurrency. Hopefully you listening now have a much richer understanding of what makes Java, well, go with Java, why it's stuck around and is still so critical.
Definitely. And if we pull back to that big picture again, maybe the most interesting thing is Java's resilience. It wasn't just the features then, it's how it adapted. But think about those core OOP ideas we discussed, encapsulation, polymorphism. These aren't just Java things, are they? They are mental models for tackling complexity in almost any large software project, regardless of the language. So maybe a final thought for you. Which of these concepts we unpacked today feels the most universal, the one you could apply tomorrow, even if you're not writing Java code? What principle transcends the syntax? That is a great question to ponder. The universal lessons hidden in the specifics. Fantastic. Well, that's our deep dive for today. Until next time, keep exploring, keep building, and keep digging into the world of knowledge.